Okay, so board exams are just around the corner. And I know that D and F block chapter can feel like a big one. But don't worry, in the next few minutes, we're going to blitz through the most important, must-know concepts that are definitely going to show up. Ready? Let's do this.
So let's start with a simple question. Think about some of the most famous metals out there. Iron, copper, gold, silver. The stuff that builds our world and fills our treasure chests. Besides being super useful, what's the one chemical thing that connects them all?
Exactly. They're all transition metals. And this is the absolute heart of the D block. If you can understand what makes a transition metal tick, you're well on your way to acing this chapter.
So here's our rapid-fire game plan. First, we'll properly meet the transition metals. Then we're going to decode their electronic secrets, because that's where all the magic is. After that, we'll uncover their superpowers, their special properties. We'll take a quick peek at the F-block elements, and finally, wrap up with why all this stuff actually matters in the real world. Let's get going.
All right, Section 1. Let's start with the basics. Who are these guys, and where do we find them on the periodic table? The D block elements are smack dab in the middle of the periodic table, spanning groups 3 all the way to 12. You can think of them as the bridge connecting the S block on the left with the P block on the right. And their number one defining feature, the thing you have to remember, is that as you move across, their d orbitals are the ones being filled up with electrons.
Now, listen up, because this is a huge point for your exams. The official, by-the-book IUPAC definition is what really counts. To be a true transition metal, an element has to have a partially filled d subshell. And this can be either when it's a neutral atom or, and this is key, when it forms one of its common ions. This definition is a classic exam question, so make sure you know it.
So that official rule brings us to a classic exam trap. What about the elements at the very end of the D block? I'm talking about zinc, cadmium, and mercury. Based on that strict definition, do they make the cut? And the answer is a big fat no. Remember that rule? It has to be an incomplete D subshell. Well, zinc, cadmium, and mercury have a completely full d orbital. It's D10. And it stays full even in their most common ions. So since that D subshell is never incomplete, they technically aren't transition metals. We just, study them here because they're at the end of the D block.
Okay, so that definition is super important. But the real key that unlocks all the secrets of the D block, well, that's their electronic configuration. It's the hidden code that explains pretty much all of their unique properties.
The general formula looks like this: N-1D, 1-10. NS 1-2. Now, you really got to pay attention to that N-1 part. It means the electrons are filling the d orbitals of the inner shell, not the outermost one. And that one little detail, that is the reason for almost everything that makes these elements so special.
And speaking of configurations, we have to talk about a huge exception that you absolutely must know for your exam: chromium and copper. See, you'd expect them to have certain configurations, but nature loves stability. So what happens is an electron actually jumps from the outer 4s orbital into the inner 3d orbital. This gives chromium a perfectly half-filled d orbital and gives copper a completely filled one. And both of those states, half-filled and fully filled, are extra stable.
So now that we've cracked their secret electronic code, let's talk about the superpowers that code gives them. These are the characteristic properties that you're going to see in your exam questions again and again.
Here are the big 5 you need to remember. 1, they show a whole variety of oxidation states. 2, they form these beautiful colored compounds. 3, they're amazing catalysts. 4, they're really strong and hard to pull apart. And 5, they're often paramagnetic, which means they're weakly attracted to magnets. And the reason for all of this? It all goes back to those unique partially filled d orbitals.
Let's dive into one of those properties with a question straight from the textbook. Why are these metals so strong? In other words, why does it take so much energy, a high enthalpy of atomization, to break them down into individual atoms?
Well, the answer is all about their unpaired d electrons. The more unpaired electrons you have, the stronger the metallic bonds are between the atoms. You can think of them like extra hands for holding on to their neighbors. This creates a super strong bond, meaning you need a ton of energy to pull them apart. Simply put, they just hold on really tight.
And what about being amazing catalysts? Like the iron used in the Haber process. Well, the textbook puts it perfectly. It's because they can easily switch between multiple oxidation states and form these temporary complexes. This basically opens up a whole new, low-energy pathway for a reaction to happen.
All right, here's another classic question you might see.
If you take a compound with copper in its +1 oxidation state and you dissolve it in water, it just doesn't stay that way. It's not stable. So why not?
The reason has a very specific, very important name you need to know: disproportionation. It turns out the copper +1 state is just really unstable in water, so it kind of self-destructs. Part of it gets reduced down to solid copper metal, which is the 0 state, and the rest gets oxidized up to the much more stable copper +2 ion. That process, where one state splits into a lower and a higher one, is called disproportionation. Definitely a keyword for your exam.
Okay, quick change of scenery. Let's shift our focus to the 2 rows at the very bottom of the periodic table, the F block, also known as the inner transition elements.
So the F block is split into 2 series. First, you have the lanthanoids. They're all chemically pretty similar to one another, and they mostly just stick to a stable +3 oxidation state. But then you have the actinoids, and, well, their chemistry is way more complicated. They show a huge range of oxidation states, and to make things even crazier, a lot of them are radioactive.
Another key idea for the F block is something called the lanthanoid contraction. It's a weird trend. As you move across the series, the atoms actually get smaller. But why? It's because the new electrons are going into these F orbitals, and F electrons are just terrible at shielding. They're like bad bodyguards. They can't block the outer electrons from the growing positive pull of the nucleus. That stronger pull just sucks the whole atom in, making it smaller.
So we've zipped through the theory, but let's bring it all back home. Why should you actually care about any of this stuff once you walk out of the exam hall? Let's look at their massive real-world impact. I mean, just look at this list. The D block gives us the iron and steel that builds our cities, the white pigment in paint, the manganese dioxide in batteries, and of course the metals we use for coins and jewelry. And the F block? Super cool stuff there too. It's in the alloy that makes lighter flint spark, it's used as catalyst to make gasoline, and it's even in the phosphorus that used to make old TV screens glow. So, if you remember just one single thing from this entire explainer, please let it be this. The secret to everything, their amazing colors, their magnetism, their strength, their catalytic power, it all comes down to the involvement of those inner N-1 d electrons. That is the fundamental principle, the ultimate master key for this whole chapter.
And there you have it. We've covered the core concepts you absolutely need. Now look around you. From the color of a gemstone to the strength of a steel game, you're now ready to see the incredible chemistry of the D and F block elements absolutely everywhere.